So now we will look at some of the capabilities of NEC5000 and also some examples that we have done at KTH with NEC5000. Just to recap, the basic idea of the spectral element method of NEC5000 is that we distribute or decompose our domain into small blocks with elements, where each element has on the order of 10 by 10 by 10 in 3D grid points, and the communication between elements is only done via the surfaces. So that means it's only the surface points that are involved in the communication. That also directly means that we only have continuity of the function value, but not its derivatives. At the same time, as you can also see from this this example, from this sketch here, we're only looking at the hexahedral shapes of the elements. So we cannot do any tensor or pyramids or anything like that. But of course, that ensures us high speed and also very good parallel scaling, because we have a high arithmetic density and only very little information that actually needs to be communicated. This we can then also appreciate when just looking at how the strong scaling of NEC5000 looks like. And this is now a numerical test that we did using this reactor assembly on a supercomputer in Sweden, where we show here the execution time as a function of processes, which are individual cores on this computer. And you can see that the total computer time essentially goes down quite nicely. You can see here a flattening out for higher numbers of processes, and essentially this is related to the fact that the time that is solved in the coarse grid solver, which is not really scaling in parallel, becomes comparable to the time of the evaluation of all the rest in each time step. And essentially, that point where you have where these two times become comparable and where the parallel scaling starts to level off, this is what we typically call the strong scaling limit. And as it turns out, for NEC5000, this is somewhere between 20 or 50 elements per core. So that means if you think of maybe 1,000 points, grid points per element, this is somewhere at around 20,000 points per core where you start to flatten out in strong scale. This is kind of an important number that we have to keep in mind. So if you would yourself like to run or use NEC5000, it's actually very simple. You just go to this homepage, and you have here all kinds of information. You can download the code. You have some documentation, maybe not very extensive, but still there is the GitHub, and there is a gallery where you can download things. There is also a lot of test or training material available online. So, for instance, we have from KTH, we have done some training or tutorials on NEC5000, which is available. There was a course with some material that you can download, and there's also some Jupyter books on spectral methods if you're interested. Okay, but this second part is about providing you with some examples of how NEC5000 could actually be used. I will do it fairly brief, but there will be references in all these slides. So if you're interested in going into more details for each of those cases, please visit the relevant references. I will mainly look at flows with pressure gradients, and it's essentially two different types of pressure gradient. The first one is kind of related to airplane wings, so where we have a bluff body at an angle of inclination, which gives us a pressure gradient. And the second one is the case where we have curved streamlines, as for instance in this example of the flow in a toroidal geometry. There's of course also other cases that one could look at with pressure gradients. So for instance, in a flat plate in a wind tunnel, where we have kind of the height of the wind tunnel changing, or you can look at more complicated geometries, for instance, this hump geometry, which will also introduce pressure gradients. And there are also cases that you could look at with NEC5000, but we're just focusing here on the wing and the toroidal case for today. So if you start with the wing, well, there's of course many different shapes that you can look at. We have now for this work I'm presenting today, we have focused on one specific wing, which is a NACA 4412 profile, which is not really a profile that is used very much. It has been used, but not really anymore. But it's still kind of a useful geometry because it represents kind of a class of wings that have useful properties, both for a fundamental study of the wing of the flow around wings, but also because they kind of resemble wing profiles that are still in use. Now, the main aspect for wings is to look at the pressure gradient, which we typically non-dimensionalize with the Clauser pressure gradient parameter beta, where we have the friction force, the non-dimensional friction force, and the non-dimensional pressure gradient. Or rather, the pressure gradient is normalized by the specific friction force. What you then can see is one important aspect of this profile is that the pressure gradient, so the beta, is very independent of Reynolds number. So that means if you change the Reynolds number and the pressure gradient, you can actually do these two changes separately, so you can study the effects independently. What we also need to do, if you now look at such a geometry, we also need to make sure that the flow is turbulent, and this we do with introducing a tripwire, so making sure that we stir the flow enough so that we get a turbulent flow further downstream. And we do that kind of with the initial generation of hairpin vortices by doing a vertical displacement of the flow, but then very quickly we'll get a fully turbulent, fully developed turbulent flow. And this way we could then set up a geometry. Here I show you the kind of the fundamental setup that we introduced in 2016, so a few years ago, where we have a wing profile and the C-type mesh around it, where we, as we said before, we trip the flow, and then we have the development of the turbulent boundary layers on the wing and then in the wake further downstream. So this was a simulation that we did a few years ago, which was on roughly 3 billion grid points. So we have all these aspects here that we considered, and for this I can also show you a quick video, which kind of shows you how this is being done. So we're using, as we said, NEC5000. For here, we try to match the Reynolds numbers that we have on the wing to what it would really mean in reality. And we came up with the comparison to a glider at the cruising speed, which corresponds to the Reynolds numbers that we have. As I said, we're doing a direct numerical simulation, so we have good resolution in all spatial directions. And then we do a C-type of mesh, a conformal mesh around the wing, and we extend it also sufficiently much into the wake region. And then we trip the flow, and essentially we look at in this video at least we look at the flow structures that develop. So we will now very soon see the flow developing, and we look at the negative lambda 2 criterion, and you can nicely see how turbulence is initiated at the tripping location. We get all these beautiful hairpin vortices that are then shed and go downstream, and they all merge, and then they follow. They build a completely turbulent boundary layer further downstream. We do that both on the upper side, where we have the adverse pressure gradient from because we have an angle of attack, where you also have a thicker boundary layer, and at the lower side of the wing we have at these angles of attack more or less zero pressure gradient conditions. So you can clearly see here that the boundary layer on the top is much thicker than below, and we have incipient separation. So we have essentially the flow is attached in the mean, but there is small pockets of separation on the upper side. And then, of course, you have these two boundary layers merging, and then we have a wake region with a specific wake effect. Okay, I guess we can move on. So what you can then do is you can look at these averages. of turbulence, so mean flow, mean pressure. For this, we have developed a turbulence statistics toolbox so that we can also elegantly rotate the averages using tensor rotation, so that we can calculate also all the fluctuations of second order statistics in the right directions. Yeah, so for instance, here we have the mean velocity, mean pressure. We can clearly see that there is a lower pressure on the top, so that means that this wing would actually fly. So here we have kind of nice resolution, as you can see. We also did some validation, so we compared this DNS with the RANS for corresponding conditions, and you can see that the agreement is, of course, very nice, which does not necessarily mean that well, it means that that the DNS and the RANS being calibrated for these types of cases can be viewed as some sort of ground truth, at least when it comes to the mean flow. This I can skip for now as well, and I can just illustrate to you what it actually means to the mean velocity profiles inside this or along this wing, just to kind of show you what the general effect of a pressure gradient would be. So if we start here at the region where we have moderate adverse pressure gradient, you can see that there is the mean profile is kind of lifted away from the walls. You have a much more extended wake region, whereas the inner region is essentially the same. And then if you increase the pressure gradient, you have an even more extended wake region. And this you can then also see that the shape factor is increasing compared to what you would expect for a zero pressure gradient case at similar conditions. So this is something that you would expect from an adverse pressure gradient case. Similarly, for the fluctuations, so the RMS values so this is at the lower position, a lower pressure gradient, and this here is at the higher pressure gradient. Also there you see that the inner region is not so different. You have a slight increase here of the RMS values, but the main difference really lies in the outer region, where you have much more energy, much more, the outer region is much more energized by the presence of the adverse pressure gradient, which you can also see in the spectra, where you even have the appearance of an outer peak for the turbulent kinetic or the streamwise fluctuations in spectra. Now, also here is a question: what type of Reynolds number can we actually reach? So the example before was a direct numerical simulation. We then experimented a little bit with also using some large eddy simulations, where we introduced just an additional relaxation filtering. So in addition to the stabilization that I mentioned earlier today, we also we increased the coefficient considerably, so that we really produce an energy sink, so that the kinetic energy of the smallest scales is really dissipated much more than it would be by just using the molecular viscosity. And this way, it was possible for us to get a reduction of around a factor of 40 in computational effort, without actually much reduction in accuracy, as we will see in a second. So the filter is, as I said before, is just kind of applying a high-pass filter again. And if we now compare data between LES and DNS in these two plots, you can see that there is essentially no difference in the mean flow, but also only very little difference in the budget if we look, for instance, at the total dissipation, which is the resolved dissipation plus what the subgrid scale model is doing. And this way, we could then produce a whole database of different wings spanning one order of magnitude in terms of Reynolds numbers, which is kind of impressively seen here by progressively smaller scales of turbulence developing on this. The highest Reynolds number, that was also a major simulation, which required the usage of Praystone. Now, of course, you can now start to wonder what are kind of the physical aspects that you can consider with these type of wing simulations, apart from just providing reference data. And I just want to show you here one example where we have tried to use our simulations to extract some physical quantities. So what we wanted to study in this case was the effect the pressure gradient has on the velocity profiles, mean velocity and fluctuation profiles. And for this purpose, we have simulated two different wings, a symmetric NACA 0012 wing and the NACA 4412 wing, the one that we see before, where we actually have some camber. And the NACA 4412 wing has a much stronger pressure gradient. So we could extract now the pressure gradient, so beta as a function of Reynolds number, and the blue one corresponding to the 4412 profile is much stronger. But interestingly enough, we actually have found one intersection point where the Reynolds number and the pressure gradient is exactly the same, but these two cases were dominated by a different history of the pressure gradient in the way of reaching that point. And this is actually something that we can now look at a little bit in more detail. So for instance, if we compare here the mean velocity profile, we see that it's kind of similar at this intersection point, but the fluctuation profiles, they're very different. In particular for the NACA 4412 profile, which is the one that actually has experienced, to go back, the one that has experienced higher pressure gradients over a longer time, you can see that there is much more energy in the outer region, whereas the inner region does not have as much energy. The same way we can compare now, so this is the intersection point that we looked at before, but we can actually also compare it to cases where we have done just constant pressure gradients, which give us probably some more indications of how the pressure gradient effect would compare to a more canonical boundary layer. So for instance, in this point number 2, where we looked at the NACA 4412 profile at a reasonably low Reynolds number, and we compare that to a beta 1 simulation, and see that everything is kind of more or less on top of each other. Whereas at this point number 4, where we have the same profile, but at a higher pressure gradient, where we compare again with a constant or more or less constant pressure gradient case beta equals 2, where again we can see that the case where we have exposed the flow to a higher pressure gradient over a longer time has a much more extensive deviation in the outer region. We tried then to quantify this with an integrated pressure gradient coefficient, beta over bar, where we can essentially see that if those parameters are similar, then the outer region would be very similar too. If those are not similar, you would progressively see a larger influence if you had a higher pressure. So this is one way of kind of analyzing what you can do with pressure gradients, or what happens in pressure gradient turbulent boundary layers. Other ways, something that you can only do with simulation data, is to look at different types of spectra. In this case, we're looking at the linear coherence, which essentially is a measure of how coherent the flow is from the wall up to further away from the wall. On the left here, you see a linear coherence spectrum for a zero pressure gradient turbulent boundary layer. This we have done with some existing data from high Reynolds number turbulent boundary layers, where essentially you can see that the coherence spectrum at the higher Reynolds numbers, the blue dashed lines, really goes up in the outer region for larger scales into the outer region, meaning that larger span-wise scales, they're extremely coherent all throughout the boundary layer. When we do the same thing now, comparing our two wing profiles, so the 0012 and the 4412 profile, we can essentially see that there is no clear increase of the coherence, even though you have in the turbulent kinetic energy, you have a clear formation of an outer peak. So you have a lot of kinetic energy further away from the wall. But this comparison clearly shows that there is essentially no coherence between what happens further away from the wall and what happens close to it. I guess this is now shown here with this yellow circle. Another aspect that we have done, and you can do with these simulations with NEC5000 on the turbulent wings, is we can look at the flow control. This was also something that we spent quite some time during the recent years, where we tried to see what are these typical control schemes that people have used in channels and in boundary layers, but how do they actually work if you apply them on wing geometries, where you're not having an infinitely long channel, but you have a certain geometry with a beginning and with an end, and typically you're not even interested in just drag. You're actually also interested in what happens to the lift. So how well is actually the wing functioning afterwards. So what we did is we implemented different control schemes, uniform blowing, for instance, uniform suction. We had a body force damping, which just aims at killing turbulence close to the wall. And then we also have blowing on the lower side. Now, I don't have time to go into details of what really happens and how the friction is really affected by these four different methods. If you're interested, there is a nice video that we produced this year, which even won an award at the visualization conference. Let me just show work. Now it works. Where I can just show you a few snapshots of this video. The interesting aspect here is that this video was actually produced with only in situ visualizations. So that means we have not stored any velocity fields on disk. We have directly connected our simulation code to, in this case, a ParaView Catalyst, and all the images were directly produced as the simulation was on. Well, in any case, what we did here in our analysis, we not only looked at the drag, but also at the lift. And in particular, we then looked at the lift over drag ratio, which is also called the aerodynamic efficiency. So the higher this number is, the better the wing is actually working. And perhaps, well, it may not be so surprising if you start to think of it, but if you now look at the results for certain control schemes, keep in mind that the uncontrolled case would have a lift over drag ratio of 44. But if you now do that, for instance, with blowing on the suction side, so blowing on the top, which is a control scheme that actually would reduce the friction, but it turns out that the pressure drag, essentially the drag induced, if you wish, by the thickness of the boundary layer, is actually increasing. And it turns out that the complete drag coefficient is increasing quite considerably. The lift at the same time is decreasing, so that means that the lift over drag is actually decreasing overall. So by performing this type of control, we are not doing anything beneficial. However, providing suction on the top means that we locally increase the friction, but at the same time, we're also making the boundary layer thinner, which means that the whole drag is decreasing by a little bit. But since we're also increasing the lift, we actually get a better performing wing, even though locally we have increased the viscous friction. And similarly, we can then look at other schemes, and it actually turns out that the best way at the end of the day would be to apply suction on the top and blowing on the bottom. And of course, this now could potentially be used in a way that you can even perform zero mass flux control. You suck from the bottom, you suck from the top, and you blow from the bottom. The second flow case that I would like to show you, where we have used NEC5000 extensively, is, as I said in the introduction, it's another case where we have looked at flows with pressure gradient. In this case, it's not the pressure gradient around the wing profile, but rather the pressure gradient that you would have in such a case, in a toroidal flow case, where you have curved streamlines because of the geometry. So in this case, you just have a bent pipe. Well, why are we interested in bent pipes? Well, bent pipes are everywhere. Actually, they're kind of in heat exchangers or these helix here, or also oil pipelines. Of course, the curvature is much different, but still, they're both kind of the same flow. What happens is, what in these flow cases that you get secondary flow because of the centrifugal effects, you get so-called Dean vortices, which essentially do a radial exchange of momentum in this bent pipe. So the first thing that we did maybe 3-4 years ago, we looked at stability, so not really turbulence, but first stability. We wanted to know, is there a critical Reynolds number for when the flow becomes unstable as a function of the curvature. Now we all know that for curvature 0, so if you have a straight pipe, there is no linear stability limit. So that's kind of, we know that from our basic fluid mechanics courses, although at the same time we know there is what we call subcritical transition. We know that the flow becomes turbulent in a straight pipe, even though linearly the flow is actually not stable. But anyway, we wanted to know whether a torus flow actually becomes unstable in a linear way. And this is what we did. And then actually the result turns out, yes, there is a stability limit. Now this is done with a slightly different code. That's not NEC5000, but what I would like to show you here is that we could then use NEC5000 to actually verify that these results are correct, so that the model that we did for calculating the stability is actually correct. So particularly we did that at the specific case, which I would like to show you here. In this case, so if you now just look at the Reynolds and curvature plot at where the curvature is quite low, at this particular position, we did the comparison between our neutral stability, which we have extracted here for the black diamond, and then we did simulations using NEC5000 to really track this bifurcation. And what we could see is that if we fit the parabola in here, which is exactly what you would expect from a so-called Hopf bifurcation here, we could see that the saturation amplitude perfectly matches this bifurcation. So that means that the accuracy of NEC5000 really was sufficient to capture this instability. In this case, or in this region of the plot where we have very low curvature, there it's exactly happening what I mentioned before, that we have a subcritical transition. So somewhere at a Reynolds number of around 2000, which is exactly the number that you can remember from the fluid dynamics classes when the flow becomes turbulent in a pipe. So this we can also, so for instance, this triangle here is an NEC5000 simulation where you could really lie on the lines of theory and experiments. So this is actually something that we also could then publish using our simulation data. But what I would like to show you here is actually a bunch of simulations that we did with NEC5000, again, related to turbulence and stability, that we did exactly at this point where we have the subcritical transition intersecting with the supercritical transition. And our question was, what happens in this critical point where sub and supercritical transition actually meets? And this was, at least we thought that was extremely interesting, because it turns out that the final simulation result actually depends on the initial condition. So let me just illustrate what happens. If we start in this critical point, if we start with a reasonably low amplitude of disturbances, we can see that the flow is quite chaotic initially, but then if we just let it integrate over a longer time, we can see that it more and more gets the shape of a traveling wave. And if you now wait for long enough, you will have here a nice periodic orbit in phase space. So that means that the flow at this intersection, if we perturb it only with low energy, would become would go back to a periodic orbit. So essentially, it would follow the way that the unstable exponentially growing eigenvalue would dictate. But what is now interesting is if we disturb the flow with higher energy, so it's a kind of a similar initial condition as before, but it's just a higher energy. We can see that we have turbulence, and then this turbulence is starting to expand, and the flow will actually never go back to the periodic or to the periodic orbit corresponding to the linear instability mode that we have seen. Now, the physical relevance here is that it actually means that we have two different turbulent or unsteady attractors being generated at the same place in parameters or in phase space. So at the same curvature and at the same Reynolds number, we have two different attractors which we can which have distinct basins of attraction, which you can identify using these simulations in NEC5000. So that means now, if we kind of want to replot from before, we actually have an overlap between subcritical and supercritical transition in this point. And as I said, this we could do with these NEC5000 simulations because of their very high fidelity of the solution approximation, that we could really distinguish between turbulence and instability. Finally, the last application I would like to quickly show you when it comes to these bent pipes is actually another way where NEC5000 was extremely helpful to us, a case where we don't look at a torus, but at a 90-degree bend. So we have an inflow, and we have a 90-degree bend, and then we have an outflow. And it actually turns out that in the literature, there was quite some interest in this flow case, because it turned out that it was observed that depending a little bit on the flow rate and the curvature of this 90-degree bend, these pipes started to vibrate. Not very much, but they started to vibrate. And the question now was, why do they vibrate? What is the reason for this behavior? It was termed in the literature swirl switching, because it kind of meant that the swirl goes from one direction to the other at a reasonably low frequency. There were a number of experiments being performed, and they did with POD some reconstruction so that you could actually see that you have this changeover of the swirl from one direction to the other. There were also a lot of, or not a lot, but some different explanations in the literature. So first, it was said that it's because you have a separation bubble, which then becomes unstable. But then some simulations showed that there is no separation bubble. And then people were also thinking that it may be related to the large-scale structure of the upstream flow. We wanted to know with NEC5000 what the reason is. So we actually set up the whole case as a simulation. And here you can see some snapshots or some video of that. So we have create an inflow with a synthetic eddy method to create synthetic turbulence at the inflow. We have convective boundary conditions at the outflow to make sure that there's nothing going back into the domain. And now we just wanted to see whether we see the same swirl switching as people in the experiments. Well, so we then decided to use POD to analyze it. POD is proper orthogonal decomposition, meaning that you would like to decompose the flow into modes which are ranked in terms of their energy, but they're orthogonal to each other. In experiments, they have typically done something that we call a two-dimensional POD. So they extracted a plane, and then they did POD in that plane. What we can do in a simulation, of course, is that we take the whole thing and we do fully three-dimensional POD, which then hopefully gives us a better understanding of what actually happens. So if you look at the what you get from experiments, So we have here the two lower rows are corresponding to experiments, one by Kalpakli and the other one by Hellström some 7-8 years ago. And they have actually kind of distinct flow structures, a little bit distorted depending on how well the symmetry of the flow was controlled. But we did the same thing now in the simulation, and we got the upper picture, where actually you can kind of start to you can kind of see that there's similar types of structures in the simulation and in the experiments. So, for instance, we have the single swirl mode. We have something that we call an in-out mode, and then we have something that's kind of an enhanced Dean mode, which you could identify. In this experiment, it was kind of mixed. It was not properly separated, probably due to some experimental issues. So that means it seems that our simulation and the experiments, they essentially extract similar types of structure. But then we start to think, what is it really that is needed to actually get swirl switching? And it turns out what you need is you just need to have the mean flow, and then you need to have these two modes, just two modes that swirl back and forth. And if you do that, then you actually get this swirl switch. Of course, it's much more kind of artificial than if you would include more POV. But the main motion you can actually get from that. So far so good. So we get the same as the experiments, but yet we still don't know what is really the origin, or what is this swirl switching. And I guess that's really where the power of the experiments of the simulations come into play. We then did three-dimensional POV. So we took all the snapshots that we had, we analyzed many of those snapshots, and we could actually identify that the main mode that is responsible for the swirl switching is actually just one mode, or actually two modes with a specific phase shift, with a specific wavelength that just are kind of lying on top of each other with an inclined angle, and they just travel downstream with a certain speed. All the other modes that we could identify were essentially the same mode, just with a higher, there were higher harmonics with a lower wavelength compared to the original wave. And this we could then also reconstruct, and we could see that in the end it's really just one mode kind of alternating back and forth, which is creating this swirl switch. Which also means that most probably this mode has nothing to do with kind of upstream modes or anything. It's probably just related to a typical instability that the flow would experience. Now, of course, in this case, not of a laminar flow, but rather of a turbulent flow. And yeah, so now you can look at the time coefficients and all of that to really see that this is just one mode oscillating back and forth. And to us, this was really a nice way of being able to simulate in an accurate way the flow as a DNS from the inflow to the outflow, and then doing kind of advanced post-processing to extract dominant modes and answer specific questions. Now, I guess I'm soon coming to the end. I just would like to share with you a few more recent developments that we have with NEC5000, where, of course, when you're interested, I'm happy to provide more details. One of those aspects is the fact that we're now being able to use non-conformal meshes in the sense of adaptive simulations. So that means we're able now to be able to split elements. So if you start from this, we can actually do H refinement by splitting elements, generating a hanging node, and in this case, being able to resolve geometric features if you need that. So, of course, this has mainly only if you think back of the matrix-free implementation that we discussed before, there's mainly effects on how this gather-scatter operator is formulated. All the other things, of course, there is some aspects for preconditioners. You need to do all the bookkeeping, but many of the things are actually very similar, or the modifications are not extremely profound. scaling is also the same. Now, without going into much details, we can now also define an error indicator, so identifying the regions where you want to refine. And with that, we can then perform fully resolved, fully adaptive simulations, as you can see, for instance, here, where the error indicator is used to identify where I need to refine, and then these simulations are being done dynamically. Now, this, of course, not a turbulent flow, but we have done it also for turbulent flows. And this is one illustration on the well-known periodic hill flow, where we have used these error indicators, trying to optimize the mesh for a turbulent flow. We have used averaged error indicators in this case, so that we can actually generate the final non-conformal mesh, which we can then use to calculate statistics over a longer time. We have also applied that for wing flows, so external flows, where previously we had to include artificial RANS-based boundary conditions inside the domain. This we don't need to do anymore if we have our adaptive meshes. And so you can see here previous mesh in red and the new mesh in black. And this is just a snapshot of how this would then look like, and how nicely things are being resolved. And our latest work now, it was that we applied this to also a rotating propeller. And in this case, this was all done with an adaptive mesh. You don't see in this plot now the mesh, how it's adapting, but there is an underlying adaptation going on. Final thing I would like to mention is also that we have been working on GPU versions of NEC5000, and there is now a number of different versions for NEC5000 available that support GPUs. In our case, we have worked on OpenACC and the CUDA version, and right now we're also looking at OpenMP. Now, without going into much detail, here you can see the scaling on multiple GPUs, where we have used A100s, P and V100s, and you can kind of see how we can actually do strong scaling. One important point here to realize is that you need to have a lot of elements per GPU for a strong scaling to work. So roughly, you need to have around 40 times more elements per GPU as opposed to a CPU. So that means we're not necessarily running faster, but we can run bigger problems. And finally, we have also been working on how should I say, a refactoring perhaps of NEC5000 into a modern Fortran version, which we call Neko, which is kind of a framework for spectral element simulations, where we can really in an object-oriented way we can construct using Fortran 2008 and modern aspects of Fortran. We can create our simulations as various objects and then solve using some of using the kernels of NEC5000. We can then do turbulence simulations. If you're interested in this, there is an archive article where we actually show results for turbulent pipe flow and Taylor-Green vortices. The interesting thing here is that we can directly use various hardware backends, so you can run on GPUs, on CPUs, or even on SX vector machine. There's of course a lot of additional features which I don't have time now to discuss that are available in NEC5000, both developed by us or by other groups, of course. I just want to mention there's a compression, there's tools for linear stability, tools for statistics, or also tools for instance, for topology optimization. And if you're interested in those, there's of course also literature that you can look. So with this, I would like to summarize and conclude my talk. So I think NEC5000 is really a mature code for incompressible and low Mach number flows in moderately complex geometries. everything is well funded mathematically, which makes it really attractive for high fidelity simulations. The formulation is very well suited for parallel simulations, and it's very efficient. And together with the availability of a lot of packages, you can really do a lot of interesting research. There's perhaps also a few, well, drawbacks is maybe the wrong word, but I would just like to say that perhaps the documentation is still somewhat limited, and there is a certain steep learning curve when you want to start with NEC5000. It's not only kind of steep learning curve when it comes to documentation, but also kind of the numerics is perhaps at times a little bit unforgiving, which is good and bad. But sometimes you have your solution blows up and you may not directly know why this is the case. Which also means that at the end of the day, you need to pay for the resolution that you need. Large simulations with high Reynolds numbers, they're not cheap. And unfortunately, there is no shortcut to that. In particular, not if you do spectral simulations where you really rely on resolving everything without compromising or without having a lot of numerical diffusion that will kind of diffuse away all your problems. With this, I would like to stop and thank you for your attention.